Okay, so what we're going to do now is to take a polynomial ring with two variables and then try to fiddle around with division, even considering very simple examples, and see the kind of problems that occur. So the kind of problems that would not occur over integer or univariate polynomial rings. So here is a very simple example. I take two linear polynomials, f and g. I would like to divide f by g and compute this small remainder. And one thing you could do is to say f is 1 times g, and then you have to fix this. So this is almost g, but then I have to subtract 2 copies of y. But this makes sense if somehow y is smaller than g. But you might want to write instead that f is minus 1 times g, and then, well, you get the y term correctly, but then you have to fix the x term by adding 2 copies of x. And this would be the right remainder if 2x is smaller than g. So clearly some choice would be necessary here to be able to compare polynomials, either 2y is smaller than g or 2x is smaller than g, and without making such a choice, the remainder is not well defined. I mean, there was no question with integers as to what the remainder had to be. There was sort of a canonical suggestion that we should take the smallest integer. Same with univariate polynomials, but not here. And what's happening in terms of quotients of ideals is the following. That if I take k, x, y and mod out by g, then I have two possible isomorphisms. I can cook up an isomorphism sending this polynomial ring to kx by sending y to minus x. So clearly y goes to minus x will annihilate the polynomial g. So this is a well-defined morphism and it's an isomorphism. So this is an infinite dimensional vector space if you want. But I could just as well do the other one by sending x to minus y. So these are subrings that I'm identifying kx by the subring generated by the first variable and ky by the subring generated by the second variable. So these are two natural projections, and so neither of them are distinguished. And that's one of the problems, that we clearly have to make a choice. And that's the first problem. From two variables onwards, there's a choice that's necessary. So this time, to demonstrate another problem, let f be the following, and g1 and g2 be these. So I'm going to divide f by g1 and g2. So first of all, we have the following. F is clearly just x times g2. So if we really want to be pedantic, it's 0 times g1 plus x times g2 plus a 0 as a remainder. So that would solve our division problem. And clearly, this is essentially the best solution. The remainder is 0. You cannot do any better. F belongs to the ideal generated by g1 and g2. And this should be the answer of whatever division algorithm that we devise. But there is the following problem, that we're going to treat this division algorithmically. Over the integers and over the univariate polynomials, we could just start cancelling out the largest terms by multiplying the dividing term. And here, if we try to do the same thing, and we will, we might as well start with g1. So we wouldn't know which polynomial to start with. So if we were to start trying to cancel this x squared y term, that seems to be the largest term, with the largest term of g1, the x squared term, then I would first do the following. I could have written that f should be y times g1, which is y times x squared minus y, plus correction now. I have to cancel this y, and then subtract x. Right, and then this suggests I get y times g1 plus 0 times g2, and my remainder is y minus x. So if we were doing this algorithmically, and we arrived at this step, there's no way we survive. We have to stop here, because y minus x will be smaller than g1 and g2, however you cut it. So it has degree less than g1, it has degree less than g2. If you do some kind of monomial ordering, you'll see that in any case the monomials of y minus x are smaller, or in any case non-divisible by the monomials of g1 and g2. So this is it. We have to stop here, and we would conclude that the remainder is y minus x. Now, obviously the remainder should have been 0, so this is already catastrophic, but the remainder also seems to be dependent on the order of how we do division. And imagine if you're trying to divide a polynomial by maybe 10 other polynomials, and we're doing one step after another, we will anyway have to do many steps, and we cannot simply keep track of every possible choice of reductions that we are doing just to see which one reaches the smallest possible remainder. So this would lead to some kind of combinatorial explosion if you had to try all possible divisions throughout the procedure. So this is a serious problem. So we didn't specify a division algorithm, we just did what makes sense. And the division algorithm seems to be sensitive to the order of the dividing polynomials g1 through, well, g2 in this case. So let's take one more message from this final example. So let's say this is the third problem, and we just observe the following. So we just computed this upstairs, basically, that y minus x is f minus y g1, but f is already x times g2. So we have the following equality, which means that x minus y belongs to the ideal generated by g1, g2, but there is no way you would have made this reduction process if you were doing some kind of algorithm. So this is just the observation from before, that y minus x or x minus y would not have been further reduced by any division algorithm. So what you cannot do is you cannot reduce x minus y further by adding a single multiple of g1 or a multiple of g2. You have to add a multiple of g1 and a multiple of g2 simultaneously to attain x minus y. And this again kind of violates the principle that we would have liked to chip away at monomial terms, reducing them one at a time. This too would make the discovery very painful, because I basically have to add to x minus y a multiple of g1. This will increase its degree first, and then reduce it by g2. And then this is also catastrophic, so I cannot continuously reduce my polynomials, but every now and then I have to increase its degree, or whatever I'm measuring by. I have to increase something and then possibly decrease further. This also makes the search space complicated. So the message to take away here is not that we will have to create a more complicated algorithm, trying to search up and down, trying to increase degrees and whatnot. The right message to take here is, it turns out in hindsight, that you cannot just work with an arbitrary set of generators for an ideal to do a simple reduction. So the problem was that x minus y was in our ideal, and perhaps we should have included the element x minus y into our ideal before we reduce other polynomials. It turns out in this case this should be enough. And in fact, that will introduce us to Grobner bases. The Grobner bases of an ideal will be the set of polynomials where you can precisely do this kind of algorithmic reduction on monomials and arrive at the correct kind of residue, this remainder. Now that we have seen what a division should be, what we expect from it, we want this ideal reduction problem, and we want to do it algorithmically. And we've seen the kind of problems that multivariate polynomials throw at us. So we need to fix them step by step. And the next thing we will do is to introduce a monomial ordering so that we can begin to compare without question what polynomials are smaller than the other ones. And monomial ordering we will do in the next lecture. See you then.